Okay, can I just get some confirmation that you can all see the screen?
We can see your screen, but actually we cannot see your video anymore. Your face is
Yeah,
gone.
let me turn that on as well. Okay, there we are.
Yeah,
Fantastic.
amazing.
Thanks everyone. Yeah, thank you everyone for being here. Thank you so much for the
Yeah.
invite. I'm so honored to be able to speak here.
So I would like to
Um,
say a few words first of all.
Please.
Today in our Next Place seminar, we have Sagar Kumar from the Northeastern University. He's going to talk about the structurally disordered communication in the population, followed by a great discussion on uh, interdisciplinary research done right. So here you are the
Mhm.
time, and then you can start your presentation.
Great. So thank you so much for the introduction. Yeah, we're going to talk about this recent paper that I just put out the preprint of, and it's in the process of um, being submitted. And it's really sort of motivated by what we're going to talk about towards the end for the bigger, broader discussion. For the sake of time, I'm going to sort of flash through some of the more mathematical sides on this, just because I want everyone to get the big picture. And so we're going to breeze past some of the details. But obviously, feel free to read the paper and reach out to me. You should all have my email. I'm happy to talk about this as much as we would like to. Okay, let's see if this will go forward now. Great. So this really, the study, the work that we've done here, and I should note that Moritz, who's on this call, is one of my co-authors and has been extremely helpful throughout the process. Um, so what we started with was really thinking about models of communication, right? And so we're talking about communication in a population, specifically mass media and interpersonal communication. And so it's been helpful to step back and think about how it all began in some sense. And really, the beginnings of communication theory started with propaganda studies in the 1940s, or at least modern communication theory starts really broadly from propaganda studies in the 1940s. And they had a very simple model. It was Lasswell. It was this guy, Harold Lasswell, that created this model. And they called it the magic bullet model sort of later on, or sometimes the hypodermic needle model of communication, which I think has a bit of a clunky name. But so the magic bullet model is called this way because the idea is that the news, whether it's CNN, BBC, whatever, they'll say something, they'll give you a piece of information, and it sort of gets directly injected into your brain, right? This is how they imagined communication occurring. And there's three major assumptions involved in this model. The first one is that it's a passive audience, meaning that the audience doesn't have to do any work or doesn't do any work when the information sort of injected into their heads. Um, it also assumes that the audience is uniform, which is to say that the same information enters every brain across everyone's watching the TV or listening or whatever, right? And the third assumption is this idea of uniform transmission, that all of the information, regardless of what it is sent the same way, at the same quality, um, and uh, and is sort of noise free in that way. Um, this is sort of the basis for what we now think of as rumor spreading models and information spreading models, which I'm sure many of you in this Zoom call, if you're doing network science or like dynamical systems or complex systems, I'm sure you've seen rumor spreading models. It's just an extension or maybe a modification of the classic disease spreading SIR models. So some of the famous ones are the Mackey-Thompson model or the Daly-Kendall model. But really, this study began with a group of mathematical biologists and game theorists um, that wanted to study the transmission of rumors in real social networks, right? And so they were thinking about networks well in advance back in the 50s. And that was really the charge was really led by this guy, Anatole Rappaport, who's quite a fascinating character. Um, and so from the mathematical modeling side, they were just taking the SIR model and saying, well, why don't we apply this to information or rumors and see if people can get infected with rumors, right? And a lot of the basic assumptions that they made followed from this magic bullet model. that the audience is uniform, that information just goes from one speaker's brain to the next, um, and things like this. There's a lot of amazing work that's being done on this still. I'm here in London right now at City University for a bit of an exchange, and right down the street at Northeastern, Jacopini, and Giovanni Petri, and all those guys are doing great work on these kinds of models on higher order networks. So really fascinating stuff. Um, but this sort of was well, a little bit of detail into that, and we'll sort of go quickly through this. Um, like I said, these are grounded in SIR models, and for those who are unfamiliar, this great diagram below from Esteban Kiss's book sort of shows that the idea is that there's a susceptible population. So in our context, it's the people that haven't heard any messages or any information yet, and an infected population. And that's those populations that have been infected with information. They've received a message, whatever it might be. And so the infected population infects the susceptible population. And the mathematical modeling for this is really quite simple and done quite well with mean field models or with mean field approaches. Um, and the idea is very simple, is that one idea goes from the infected to the susceptible without any noise, without any loss, anything like this. In disease modeling, you get sort of fancier ones. Right now, we're not interested in those, but it's something to think about. You know, besides just being susceptible and infected with information, what other states could you possibly be in? But this sort of runs contrary to what was happening in communication theory at the same time as these models were being developed. In fact, actually, maybe even 5, 10 years prior. Um, so in communication theory, in this literature, this sort of took a more critical approach, first of all. And it was really, instead of being grounded in spreading models, was grounded in the information theory of Shannon and Norbert Wiener and Weaver that had just come out not too much prior. So the information theory work really relies on this idea of noise, right? So how much information can be passed from the source to the receiver, given the fact that there is noise in transmission. And so this informed a lot of work in linguistics with the whole Prague School and Roman Jakobson and Levi Strauss in anthropology. And the idea is quite simple, is that the Shannon-Sell information theory suggests that we should be or could be thinking about language or messages or anything as a set of possible codes, right? So there's a thought, and the thought gets encoded into language, and then that language is transmitted from your mouth into someone's ear or, eyes or whatever, if it's television, and then gets decoded out of language back into an idea, right? That's sort of the basic premise of both Shannon's information theory, but also Stuart Hall's work on the encoding decoding model. And so the big difference here is that while information spreading models were sort of more focused on, okay, how does information sort of in a particle-like way transfer from one brain to another, to another, to another, the communication and information theoretical literature was more interested in, well, how are messages distorted? How are messages encoded, right? And so sort of even before information spreading began, there was already this work thinking about how it doesn't really make sense to think about information as jumping from one brain to another, because signs are not just passively received. They're not uniformly transmitted across populations. Individuals all receive signals and decode them in slightly different ways. And so from a mathematical standpoint, we might think about this as suggesting that mutations in the thing that is spreading occur at the same time scale of the spread, which is not something that is built into any of the spreading models, or at least not the ones that we were talking about. So like I was saying, this is grounded really broadly in Shannon's model of communication. And we don't have to get too deep into the woods on this, but it's quite simply that it's a Markov chain based idea, right? So it's just a Markov process where you have one sender and one receiver, and the sender will send message A with some, they'll encode message A, and then it'll reach the receiver with some probability. So it's no longer the fact that message A goes straight from sender to receiver. It's that message A with some probability reaches the receiver, but also it may get sort of caught up, entangled in what we call a noisy channel. Um, so for this study, we're specifically interested in discrete noisy channels, and I'll show you what that looks like in a moment. But the long and short of this is that when a message is passed from sender to receiver, it's not an exact replication. It's a noisy process, and there's some loss in that. Um, and if you believe this or not, or if you don't believe this, I always say we can just play a game of telephone. And I promise you, if you do that with your friends with a chain that's, longer than maybe a handful of people, you're not going to get the same message back. It might be completely different, really. Um, and so that in and of itself is sort of an empirical heuristic that we can use to say that, yeah, there is something to this idea of information loss when it comes to information spreading. And it's quite important also, not just for, as a fun game, but also there's a lot of great work in communication and literary theory suggesting that this sort of distortion is an inherent part of the communication process. And it actually is what leads to not just misunderstandings, but also misinformation, polarization, and discrimination. So we have this schism between in communication between models of information spreading or rumor spreading, which still assume the old magic bullet model, and the work in communication and cultural studies that began the magic bullet model even before rumor spreading models existed. you know and so the problem that we're facing is this question of how do we unite these approaches to develop a model of communication that doesn't fall prey to the assumptions of spreading models, but still has the ability to capture the dynamics of information being transmitted through a population, because that's still a very useful thing to do, especially when we're thinking about information campaigns for vaccines or public health or anything like this, right? Are there any questions so far? I always like to stop here because this ends the background section. Okay, feel free to ask as we go on. Raise your hand in the Zoom, but I'll leave some time for questions. So just as a quick diagram, just so you see it, the original sort of magic bullet model you'll see is sort of what we see on the top, where there's a sender and a receiver, and there's this little ball, which I'm calling a message, that's transferring the internal state of the sender to the internal state of the receiver. In the information theoretic case and in the communication case that we're going to be using, it's more like the bottom, where the internal state of this sender is this orangey color, and they encode this message. But there's a channel in between them, which could cause this to flip, right? So the channel in between them is sort of a classic binary symmetric channel. And so with some probability, this orange message flips into a purple message. Usually the probability is low empirically, but it's a non-zero probability. So what we do here is we basically take what's on the bottom here and stick it on every edge. Sort of every time there is some sort of transmission from from an infected to a susceptible member of the population, we say that it's the same as always, but there's some probability that there's going to be a sort of structural distortion in this way, that orange might flip to purple, right? But it's a little bit more subtle than that. So we're really trying to model communication as it's defined, as it's understood from an information standpoint. And so we imagine that we have some source, W, and the source is in some state, right? As of right now, the state is omega, as you see on this first edge. So we say that the goal of communication is that there's some small finite fraction of the population that observes the source. And this small set of observers is trying to inform the entire population of the state of the source. And so the source is in state omega, and so they encode this in their own way. And now 2 out of 3 of these observers encode omega as being this orange message, but one of them encodes it as being this purple message, right? And this E omega orange is just our way of stating this is the matrix. It's a stochastic transition matrix of, the probability that omega will be encoded as orange, right? And then they go about this process that we've shown of like they're spreading it from person to person, and the probability that it's going to get distorted from purple to orange is captured in this Q matrix. So we'll take, for example, the top spreader in this set of observers, they have encoded this as orange, but one half, one of their messages goes through sort of as we would expect correctly, but one of them flips to being a purple, right? And that's sort of what this model is. It's happening at every sort of infection step, is we have this probability of distortion, and the distortions are structured in this specific way, where we have five different channel sort of types or topologies. So in one case, we might imagine that the orange message, message one, gets flipped to message two with some probability, and the same is the case in message two. But we could imagine that there's three messages instead, and we get to this triangle section. So, they all flip to each other with some equivalent probability. It's all symmetric. But what if we have the case of the cherry section where message one could be distorted to message two or three, but two cannot be distorted into three, right? So we have all of these possibilities, and they can be sort of understood through the top formalism, which is called a confusion graph, or more classically, the bottom formalism is just a standard channel diagram. But we're treating this in a discrete way. We imagine that they can encode these messages as one of a possible set. Um, I'll point out the binary symmetric one is quite fun as well, where we have the same case where message one could be transmitted through res regularly or flipped to message two, and message two could do the same, but the probabilities are not the same. So message two is less likely to flip into message one than message one is to flip into message two. So we have these different possibilities, and you can set up these channel configurations however you want to. The paw channel is quite a fun one, or champagne glass, as some call it. So I will shout out that there's existing work on this in epidemiology. Guillaume Saint-Onge, who's at the Roux Institute at Northeastern, did some amazing work on mutations in disease spreading. They do it a bit differently and answer different questions, but it's definitely related and quite interesting work. Go check it out. This work in chaos was quite an exciting piece. They do something similar as well, but they're more, they sort of define information in a different way, and they're a lot more reliant on these ginormous simulations, but it's also quite an interesting paper. And actually, as you'll see, we sort of recover some of their results, but actually explain them a little bit more. And then finally, there's all this work in network information theory, which, to be honest, is maybe the most direct extension of what we're thinking about. They've been doing this work since information theory started, but they don't do it at the scale of populations. It's more like two or three senders and receivers. And the reason for that is because the methods in network information theory are like very exact and really kind of infeasible to take at the scale of a population. So what we're doing here is, to make it a little bit easier, we're just creating a mean field model. And we're doing this in the way that the SIR model does it. So pretty much this just extends an SIR model, both in the stochastic simulations as well as in the mean field approximations. And basically all we've done is we take the SIR model, drop the R, we're only cared about the spreading. We don't have any recovered compartments. And then we take our code, or we take our channel, our noisy channel, and we say, okay, well, if someone spreads message zero, then there's some probability it flips to one, some probability it flips to 1, 0, right? This is just our little cartoon for a noisy channel. Basically, what we do is we just stick it in the I compartment, right? So every time there's an infection, we allow this sort of noisy process to occur. This is the stochastic model. Take a look at it, screenshot it. I don't care. Just, I'm not going to go too much in depth about it, but basically the top one is saying that there's some, the probability that the source omega is encoded as alpha is this. The probability that someone goes from susceptible to infected with alpha is this. And then there's no possibility of someone who's infected with message L to go to being infected with message alpha. This is where our mean field model comes from. And so I want to point out is that this is just the spreading portion, right? This is literally just an SI model. Without the second I, without the quadratic term. And that's because the second, what would be the infection part is tied with this Q matrix, which is just, like we were saying earlier, it's just a stochastic matrix. So you can sort of think about this as being two parts put together, right? It's a spreading portion coupled with a random walk. And so what's happening is the random walk is happening over those channel diagrams, not in the population. So you can imagine those channel diagrams that I was showing earlier of the martini glass and the triangle and all these things. One way to think about this, instead of thinking about this as a noisy spreading process, is to think about it as a random walk with a logistically increasing uh, number of walkers. I don't know if that makes it less confusing or more, but it's one way to go about thinking about it. But what's important here is that we're going to think about how do we take, oh, I should state also that this phi, this is our number of sort of infections. This is our number of people that have received any message at all, and it's a vector broken down by message. So, you could imagine a vector of like zero point 0.2 in column A and zero point 0.3 in column B, and we'd say that half the population has been infected, quote unquote, and 20% of the population's been infected with message A, 30% with message B. So this is just our state vector. So the question is, how do we get information out of this? Well, we basically, and I'm going to skip through this a little bit, we can basically take that state vector and transform it at any point in time to get a mutual information. And what we're calculating, crucially, is the mutual information between the state of the entire population at any time t and the state of the source. So we're asking this question, if we surveyed everyone in the population, everyone that has received a message at time t, how much of a signal does that give us? How much information do we gain about the original state of W based on that? And I'm going to skip past the questions just so we can get to the results, and then you can ask away. So using this whole formalism, what we're going to ask is, given a noisy encoding channel and a noisy peer-to-peer transmission channel, the way that we showed in the model, how much information is received by a member of the population? And we say the last person just because that's when the whole process saturates, but you could ask this question at any point in time. Okay. So before we get to the information, this is just sort of a bird's eye view of the dynamics of messages in this model, right? So as you can see in the first, we'll focus on the furthest left column on the top left corner. This is the fraction of the population that has received either the red message or the blue message. And this is the fraction of the population that's done so when the rate of distortion is 1 out of 100. So 1 out of 100 infection events, per se, flips. And you can see that it's actually the original message seeded is always going to be the red one, as that's the starred message. And the red one sort of is dominating. But as we go down the line and we increase the error, the likelihood of distortion, you can see that just out when it gets to 2/10, it's almost even, right? But crucially, it's not exactly even. It's not necessarily crucial, but it's not exactly even. And as we can see, as we get to more messages, it sort of isn't the case anymore. We sort of lose that. They decouple a little bit more, and even more so for when we get to the paw channel. But when it's fully symmetric in the triangle, then we sort of see this evenness again. So we can sort of see this idea that more symmetry leads to like more evenness in the messages as error goes up. Also quite interesting is that we see this idea that structural equivalence in the noisy in the channel configuration sort of leads to a dynamical equivalence. And that's to say that if you can see here, the yellow and the blue messages in the triangle are sort of structurally equivalent when related in relation to the original seeded message, which is the red one, and they track each other almost exactly the whole time. Whereas in the case of, for example, in the martini glass sort of paw channel, you see that none of these are exactly structurally equivalent, and so they're all remaining separate the entire time. And this becomes a crucial insight as we go further and ask about the information. So looking at the dynamics of information, on the top here, the top beige line, we're using just a standard multi-strain SI model, right? This is the lossless case because there's no error in an SI model, just a standard model. So what we're seeing, and this is just so you guys know, in both of these, the shaded regions are simulations using a modified Gillespie algorithm, and the dotted lines are always the mean field approximations. So as you can see on the top here, both in simulation and in the mean field, there's no information lost besides any information that was lost in the initial encoding step. And we can talk about that later, what that means. But it's pretty even the whole way across, right? You can always reconstruct the state of the source the same across any point in time because there's no information lost. However, when we look at the bottom beige curves, right? These are the curves for what we would consider like like a structural communication model, more of an information theory based model. And for those of you who are familiar with like Ising models or opinion dynamics models, this is effectively that, right? In a continuous time. Um, and so we're asking this question is how much information is left at time t using one of these sort of Markov process models. Um, and it dies off like quite quickly too, right? And so what we can actually show is that it always goes to zero for any well, for anything that's not this asymmetric channel. And that has to do with the property of random walks and Markov processes, right? But no matter what, it'll always go to zero in anything that's these kind of when you have symmetric edges. Um, but our model is the one in purple, right? And so on this top half, this is when the error is at 1 in 100, and in the bottom half, the error is at 7 in 100. Um, and on the right side, they're delineated based, this is the amount of noise in the initial encoding. So the amount of noise in the initial encoding basically just drops our x axis intercept, or sorry, our y-intercept. And the amount of noise in the actual peer-to-peer spreading, as you can see, sort of makes the decline much sharper. What's important to say here is that, these two models, the SI model and the Markov chain model, what we're calling a structural communication model, these sort of constitute the two extremes, right? Either full information preservation at the top, or just total loss of all information at the bottom. But what our model does is it sits in between and it's sort of tunable, right? So we can ask, like, compared to when we've started, how much information is left at the end? And we can sort of tune the model to fit that. Um, and it decays, as you can see, like the structural communication models, but then hits an asymptote just like an SI model might or a rumor model might. And the reason for this, for those of you who might be inclined to like electrical engineering and all of these things, is because we have a process of amplification happening in the spreading models. Because spreading models, if you infect one person, you're not just done after that, you keep going. So there's this idea of repeaters in this signal chain. Uh, but yeah, the good news is that it all obeys the laws of information theory. We're all happy, it satisfies the data processing theorem. We're all good here. So the question now becomes, well, how quickly do we lose information? And does it depend on the channel? And it does. It matters quite heavily on what the channel configuration looks like. So as you can see, well, before we get to that, on the right side, I haven't talked much about encoding sort of intentionally, but so in the encoding step, it's pretty straightforward. It follows just a classic, sort of the classic curves you would expect for a noisy channel. It's a linear relationship between, so the amount of information in the encoding is linearly related to the amount of information at the sort of end of the spreading process. But the actual drop is exponential. So we lose information exponentially compared to the beginning. And it depends on what the channel configuration looks like. So what we learn is that more symmetric channels, such as the binary symmetric channel, lose information much faster than less symmetric channels. And you can see that because the binary symmetric channel in the blue loses far more information than the binary asymmetric channel, which is these little orange circles. And you'll see that I'm measuring this as the capacity instead of the capacity of the channel instead of the actual mutual information. Again, kind of a technical detail, and we can talk about that. But this is the capacity of the whole spreading process. So at the end, once spreading is saturated, what is the capacity of this whole process when we're thinking about how much information comes from the source? Also, an important fact to note is that the only time that there is zero, because it decays very, very quickly, right? It decays very, very quickly. But the only time that there's mathematically zero, according to our mean field, is when there is zero information that's actually been encoded at the first step. So it's only zero if you don't get any information at the time of reporting. If there's any information at the time of reporting, then you'll have information at some non-zero information, regardless of the population size. But again, that's the mean field model in a homogeneous setting. It could very well be quite different in structured populations. I'm working on that right now. This is just the proof that there's only one zero, and it's also proof that whatever the initial message that has been seeded, whatever is the majority then, will remain the majority throughout the entire duration of spread. So if message A has been seeded, by 6 out of 10 observers, then it's always going to be the most populous message in the population, even if the rate of error is 100%, right? And that has to do with the property of this dynamical system specifically. Okay, but we don't have to go through that now. Let's just go through the implications and then we'll move on to the questions in the next section. So what we learned from this is that when we're thinking about social learning, when we're thinking about communication processes, what we learn primarily is that spreading is a necessary component when we think about mass communication, when we think about mass media especially, right? Because if we just treat it as an opinion dynamics model or a Markov chain, it's not going to work, what they call a linear communication model. It's not going to work very well because it's not thinking about that spreading process. And what we learn is that the spreading process adds memory to it, right? It's no longer Markovian. And that's because of these repeaters, because of this amplification that happens, which sort of limits the amount of information that can be lost. It also this work sort of also nods to a validation of early communication theory from Stuart Hall and Marshall McLuhan, and some other theorists that talk about how important the initial encoding is, right? Because it's the initial encoding that we've seen in this model determines whether or not there's information at all and what the most populous message is going to be. Regardless of how hard the population tries to shift that message away, if it's the most highly seeded at the beginning, it's going to be the most highly, or it's going to be the most concentrated, throughout the duration of spread. Like I said, we prove some stuff, or not prove, we sort of, verify some stuff that was in the Tian paper in Chaos about information invariance, and we sort of go a little bit further and sort of provide an explanation for this. And all in all, this is sort of just my plea to say that we should move away from spreading models when we're thinking about virality and we're thinking about communication, at least in the context of written and linguistic communication, and more towards models that measure information and not just the spread of a message. There are some practical considerations also. So we're working right now on developing empirical studies that could show that this works and it makes sense, or it's at least, the shapes looks the right way. And so I think that could be easily done using some sort of, with collaboration with some media and literary scholars that are sort of very good at developing these discrete codes. And that's been done for the last, they've been doing it for the last 70, 80 years now. And echoing sort of the work of Stuart Hall again, there is this sort of tension that this shows between sharing and understanding and retaining information, right? Because we often compress things to make them easier to transmit from one person to another, but that also causes loss. And sort of finally, besides the implications that this has for disease spread, if there is a disease that mutates at the same time scale as spread, which there are quite a few, the sort of real implications for this lie in like studies of propaganda and misinformation, because this would suggest that it's not through preventing peer-to-peer communication that these things should be fought, but instead they should be fought by sort of protecting a diversity of journalistic sources. And that's all I've got for you for that.
Thanks, Sagar, for your great talk. I would like to say, if you have questions, you can raise your hand and also unmute yourself to ask your questions. Okay, I may start with a question. I would like to say this work reminds me of those models about the innovation networks. For example, if you would like to see if two person collaborate with each other, this like a collaboration tries to like create a new complexity. I mean, you were like coding like how like these zero ones are like mutuate to like something more complex or less complex, like these kind of things. How do you see like these models can be adopted into the innovation, especially in science or like, I don't know, in the patent analysis and these kind of things? Because it's not only in the news and like media, it can be also adopted somewhere else.
Yeah, no, I think that's a really great point. And thank you for bringing it up. Definitely, the mathematics, this is inspired by communication and media, but the mathematics sort of extends. Um, so I'm actually working with some people at CEU, well, one person from CEU, and some others, uh, and we're thinking about this process of what's it called? Combinatorial evolution, right? So, like you're saying, it's not this evolutionary process that's Darwinian, but more on the innovation front. And innovation we've seen, from the work of like Brian Arthur and all of this, that it makes more sense to think about it combinatorially. So actually, this is a great question. One of the use cases that I've been thinking about playing with, and I'm sort of talking to some collaborators about playing with, is in the context of like fashion and innovation in that way. So we've got this project that we're already working on that is related to innovation and evolution of fashion trends and things like this. Um, but definitely, I have been talking about trying to use this model in a combinatorial evolution way. At the end of the day, it's not the same thing as combinatorial evolution, right? Because that is still not a noisy process, but they're definitely related in a lot of ways. And what's really exciting about the innovation models and the sort of combinatorial process is that it includes the sort of binary interactions that I shied away from a little bit at the beginning, right? Because I don't allow, if someone's spreading message A and someone else is spreading message B and they interact, we don't allow that in this model. Mostly because I didn't want to have to define an algebra or like anything like this
Mhm.
on the set of messages, right? Because
I
then
see.
that becomes necessary to understand what happens on binary interactions. But that's sort of the primary difference, right, between this and
Mhm.
the innovation models is they are sort of willing to
Mhm.
say, okay, when you know this thing and this thing come together, this is what is going to come out of it.
Yeah.
I'm a bit more hesitant to do that at this stage, but it's definitely it's interesting and related process.
Mhm. Is any has anybody like a short question? Because like I think we have like a very long question from like Julia. So before addressing that question, maybe we can try to address another short question.
Mm,
Okay.
I can maybe ask a quick one.
Yeah.
Um, uh, Sagar, you were mentioning that right now what's going on here is you have like a structured population, like this kind of growing space of people. Have you thought at all
mm,
about like different kinds of networks that this communication process takes place on, and how that might
mm.
change the model at all? Hopefully, that's not a long question, but
No, no, no. I mean, it can be in the sense that I'm starting writing on that right now, but and no, I do want to answer Julia's question actually. But so uh, I have a bit, and I think my suspicion and what I'm testing now is that you will probably lose less information overall in structured populations, specifically in sort of these power law type networks, because you have a mass of people that are holding on to and promoting the same message over and over again to a large fraction of the population, right? If you have these hubs. I imagine that in an ER network, it's going to be the same as homogeneous, more or less. But I imagine this sort of small world effect will definitely, think about how internet routers are set up, right? In some way, it's what they're trying to do is prevent information loss, and so they set them up sort of in this scale, in this power law way, so that you have these signal amplifiers located in places where they can amplify the signal to the most things most efficiently and prevent loss in this way. So I think definitely as we add structure to the population and we add a heterogeneous degree distribution and you have these sort of high degree nodes, you'll lose less information. but I'm excited. The math gets a little bit trickier there, but I'm kind of excited to see if that's right. Thanks.
Very cool.
Julia,
And yeah,
Julia,
yeah.
go ahead if you want to ask your question.
Cool. Thanks for the talk, Sagar. This was very cool. So I was wondering, it seems like there's kind of a general assumption that a language change happening is noise or a bug rather than a feature. So I was just wondering, it
Mhm.
could be perceived as goal directed because we see like these patterns of how language change happens to sort of smooth ease of like producing sounds in like phonology or in lectio difficile or potior, which is like from if you're translating various texts, then the more complicated reading
Mhm.
is perhaps the more authentic one. So I was wondering in that case if noise could be goal directed or serve a purpose, what would it change if you incorporated that into the model, do you think?
No, I mean, I think that at some level, sort of philosophically, it that is the whole reason that this exists, right? Like that's what I was hoping. I think this is a feature of language, right? I think it's not just a feature of language; it's also a feature of reporting and journalism in general. But um, I really revere and sort of appreciate that fact about language. So it's not necessarily like a bug. And I know when we're talking about it from a mathematical standpoint, it seems this way. But I think this sort of, not even when it comes to language change, but like the rhetoricity of language, even, right? So it's like when we think about how something changes, not even, I mean, of course, for something to change rhetorically, it has to change syntactically. But even if we think about the same information, quote unquote, underlying being changed in a rhetorical way, I think it is goal serving and I think it does serve a purpose. And I think one part of this project and one part of this is not to say that, oh, this mutation occurs as a, you know, again, it's being modeled as a stochastic thing, but that's supposed to be hopefully some sort of proxy for an aggregate, right? More so, the point is that different individuals are goal oriented in different ways, have different values, blah, 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 blah. And so what they get from a message, from something that they see or something that they hear, and what they repeat out of it is going to be aligned with their goals, with their values, with all of these things. And so it's not necessarily that the language change is a bug, but it is a feature of how we communicate with each other. And actually, this ties really nicely with the work that Stuart Hall did, saying that the whole reason we have to think about the encoding and decoding and noise in language is yes, there's some level of like, oh, I misheard you. You know what I mean? But there's also this level of like, well, Republicans and Democrats are going to say the same fact different ways. And those, instead of thinking about something in this channel being true and false, we can think about it as being, oh, a Republican framing and a Democratic framing. Or we can think about it as being a leftist framing and like an alt-right framing. Or we can think about it as being pro cats and pro dogs. You know what I mean? Um, so it's not, so this can be thought about in a way of like, oh, I just misheard you, the words are wrong, the syntax got jumbled up, like I thought I heard 42 and it was 52. That's one way to think about this. But another way to think about this is saying, well, I told you I had a red cat that eats food at night, and all you heard is that I had a red cat and something about the nighttime. And so you make up that second fact. You know what I mean? All you care about is the cat. I don't know. You know what I mean? Um, so yeah, I definitely do. I definitely think that at some level, the goal directedness is a part of this. How it would be done. So what would is an exciting question that you're asking also, I think, is how does that change if we sort of give these people the goals, right? In some sense of like um, each person has their own noisy channel and like based on their goals or something. I think that's quite an exciting question, and I think it's something that I've been thinking about a little bit, especially when we're thinking about simulating with, you know, agents or something like that. I definitely think that it'll definitely, again, reduce information loss more than we think it would in just a random setting like this. I think you definitely see sort of more siloing, more polarization and all of the, you know, quote, polarization, quote unquote, in the messages. Um, but yeah, I think the goal directedness
Yeah.
and language are really closely related in general.
Thank you so much for everybody, for your questions. It was a great talk. So before moving on to the second part of the talk, we would like to say that NetPlace has joined other complex system societies to create an umbrella organization called Core. I put the link to the website in the chat. You can also join the Discord channel, and then also you can see there a lot of resources. You can ask your questions and also find job opportunities, and also all the kind of seminars I don't know, workshops and conferences, deadlines, these kind of things. They are there. Okay, moving on to the second part. Do you have slides to share?
No, this was just, I
Okay.
was just thinking this could be a conversation.
Yeah.
Yeah.
Yeah, great. Okay, so you can start.
Great. So I just wanted to talk about interdisciplinary research, sort of more broadly. Um, and specifically because I think in complex systems and in network science, we are often given this luxury of exploring all the things that interest us, as long as we sort of stick to a general complex systems framework. And I think that can be really great. But I also think that as a young PhD student, when I was starting, it was really difficult in the sense that it was hard to put my roots down or nail any single thing that I wanted to focus on down. In part just because all of the methods are so shiny and exciting, right? And so you want to focus on these oh, I want to use an SBM, I want to use this PID sort of thing. I want to do all these things. Um, and you sort of lose track of what you actually want to be doing. And in a lot of cases, in a lot of settings, doing some work now in epidemiology and psychology, um, those methods don't really fly at some level when you're publishing. It's like people are quite skeptical about them. And so I wanted to talk a little bit about what I found to be the most useful thing, being really focusing on starting with a question and trusting that you'll get to use whatever cool methods you want to use, and you'll get to use all the fancy complex systems techniques. That sort of comes from just being a part of this world. What really is difficult when you're in complex systems is not devising a method, but it's coming up with a question, and coming up with a question that sort of suits your interdisciplinary interests. I just want to know, how many, have other people felt like it's been difficult to find a question, or has it been quite simple for most of you? I don't know if your advisors say this is what you have to work on.
I mean, you addressed a very great point. You say okay, I would like to focus on a method and then I find a question. For me,
Yeah,
it was all the time the opposite. I have the question I would like to answer, then I just try a bunch of methods. Mostly some of them they don't work, and then my question is adapted through the time from the responses I get from the the analysis, and then the question changes all the time. It's not
yeah.
a single question that I would like to answer. The question is quite
Hmm.
dynamic and tries to find its way as the research time changes. So I would like to say maybe I see it from another point of view. Maybe the method is not shining for me. It's the idea that is flowing around. So yeah, so maybe
Well, that's quite nice.
yeah.
Do you feel like you are quite focused on sort of the general thing that you want to think about, even if the question isn't so laser focused?
Now the point
Yeah.
is, if the question is flowing, it can go anywhere, and that's the point.
Yeah,
Maybe
right.
you want to address something and then you are interested in something, but something that you publish or you just get out of it, it's not the thing that you wanted to focus on it. It's the question
Yeah,
flowing
right.
around, and that's not really the best practice. You want to think on something, but the world
Yeah.
doesn't allow you to do so, or maybe
Yeah,
yeah.
right. Right.
Yeah, so
All right. Yeah, no. And I think that's sort of what happens quite often. I think you're right. I think the question does mutate and change in itself. Um, I think one of the tough parts, so right now I've been working with some psychologists doing some exciting work. And I think that has been a big culture shock in some sense. My background's in physics and philosophy. Neither of those follow the methodologies of psychology, which sort of does things in its own way. And I think that's been quite a big culture shock to see like how they go about, pre-registering all of their questions and hypotheses and methods. And sort of again, how I feel like that's one venue where, suggesting to do something that's outside of, you know, statistical analysis that relies on like normal distributions and all of this stuff and regressions is quite difficult. Like people don't like that. Um, but I think it's been an excellent it's been an excellent project in saying, okay, the question is maybe more important than the methods, right? Because at the end of the day, if the question and the data and all of these things work out, then you get something quite good, even with, linear regressions. Um, and I think that was a bit of an eye opener for me. Has anyone can I get some sense, like even in the chat, like what general fields people are in, like outside of complex systems and networks? If you do maybe like pure networks, then say math or something. Oh, thank you, Gabriela.
Hello, can you hear me?
Oh, yes. Hello.
Okay. Uh, yeah. Hi. I have a experience that's quite, I think, interesting. Because like my background is more in engineering, electrical engineering, control theory,
Mm,
dynamics, machine learning, and that was my project was created in a way to mix uh, chemical complex systems, so chemical reactions,
mm,
with high order
mhm,
networks. But uh, my advisor is a chemist, a experimental guy. And so he knows
mm,
very little about computational methods.
mm.
So I'm working in a lab of experimental people. I'm a complete alienation there. I'm a complete alien there. So
Oh, yeah.
it's very weird, but also it's interesting to see this type of thing because when I came here, I realized that the notion of networks from my advisor was completely different from my
Mm,
co-advisor, that's mathematician, and my concept of networks. So I need to rethink the project in a way that makes sense for me to work with that. And I was thinking, okay, let's do something with the high orders, trying to put
mhm,
chemistry with that. But it was so difficult because none of us are trained on high orders. For us, it was quite new also. So we started doing small stuff from network things
mhm,
to understand a little bit of chemistry. So our first work is a
mm.
little weird for me because the question was very difficult to find because we are trying to mix two things that was not talking, but they kind of cite each other, but they're not really talking. So when I present my work for network people or complex system people, it seems very simple. Like I don't think
Yeah.
I could put too much to them. But the perspective of my advisor, what we did in his field is important. So sometimes it's difficult also. But
Yeah.
I think also this idea of it's nice to have an idea of what to investigate the question, and you start trying some methods, and with this way, I think you shape your question in a way that makes sense. That you can
Yeah.
finish a
Yeah.
paper, for instance. I see a paper as a dynamical system that you're changing with a lot of loops and something like that.
Yeah. Yeah. I think that's absolutely right. And yeah, I see the chat also talking about starting with the methods. And I agree with that. If you're developing a method, I think that's a great idea. I think definitely like Yasmin was saying, the trouble comes when you have a method you want to do and you want to apply it to a thing. If you want to study the method and you want to build the method, I think that's a great thing to do. I think that's quite important. But what you're saying also is like I sort of experienced this trying to do some work with complex systems in a very small niche of evolutionary biology, right? Where there again, it's sort of um, they have the way that they're doing things, and there's definitely always pushback when you're modeling these systems that have a very specific way of being modeled. And I think that that pushback should be listened to at some point. Like, I think that's an important thing to hear out and sort of be like, okay, these people have been doing it this way. They know what they're talking about at some level. But definitely, it is difficult to sort of sometimes even just translate like what you're doing to a community that or to a discipline where it's not the norm. And like you're saying, Everton, like it's funny because in the complex systems world, in the networks world, sometimes it's sort of like, very easy, nothing groundbreaking. But in other places, it's sort of is out of left field a little bit. Cool. I also love that there's so many. I mean, I've seen at least a couple language people in the comments, which is good to see.
I mean, I can try to read some of them. Like Gabri said that the problem is in fact focusing on the right questions, then you find the appropriate methods and the people to collaborate. And Julia
Mm.
also said, to be fair, a methodology can be a question it's in its own right. So nothing wrong with starting with a methodology. Yeah, good.
Mhm.
And also, Eric said, as a methods person, I agree. Sometimes people limit their question based on the available methods, especially in the writing procedure. I think it's all of them. They are really good comments. I would like to say something else. Like there was like a conference in Zurich like last year that like a girl presented her work and also like said after that. Yeah, do you think that because I applied only linear regression to this model, it's like the project is not getting enough of attention? Because there are super fancy
Mm.
methods to do a lot of cool things and you can get a lot of results as well. But like nowadays, like you feel like maybe you're falling behind if you don't use like a very fancy methods. So that's also something, specifically like in many fields, like I don't know, like computational social science. I don't know, maybe even like epidemic is spreading. Like people are trying to make more and more complex methods and like this kind of thing. So this fear of like falling behind the trend, it's really real. So
Yeah, I think that's sort of what I think that's really what I was hoping to get at. Because definitely as a young PhD, I think that was the big fear. Is there's these things that are interesting, and it's either it's not just, oh, I can contribute to this method in its development. Well, I don't know enough about it yet. But if I don't use something quite as fancy and new, then it's not going to be taken as seriously. So I definitely think that that's a real concern.
true, true. Anybody has any other comment? So if not, I would like to thank Sagar for your great talk. It was really interesting and also very nice aspects, like merging the two aspects of like spreading models and also like the information theory. Great. Thank you so much. And thanks everybody for being present here.
Thank you, everybody. I appreciate the chance to talk. Have a great rest of your day. And